So how was the midterm?
Okay.
Okay, was it how about the were the questions reasonable? Let's begin with that. Let's say so.
Apart from this,
Apart from this one, no, reasonable in the sense not whether it was easy or hard, but was I reasonable in expecting that it should be doable, or was it too hard? Right. So that's I mean that's feedback for me. Like it helps. And then comes was it? That's the first time I asked that question, so it is possible that I didn't know that exactly how students would respond. But having gone back, did you get a chance to understand how that problem?
I actually look for in websites and other stuff.
Probably not. Yeah, I just created out of the blue. Yeah, so often sometimes the wordings confuse and all that stuff. But now is it clear what is to be done, or should I go over it?
It will be helpful if you.
Yeah. Okay, so I could surely do that. Okay. But before that, I get the impression that most of you do not understand contour integrals in the conceptual sense. Like most of you get like except I think Ken, I think you have done decently better than others. I think I can take names here, right? We are only 4 of us. I think the statistics of the grade statistics for 4 people really is giving away too much. So I think if you don't mind, I think like you can do better always, everyone. So, but I think most of you like need to understand contour. So there is a or what I'm meaning to say is that see, one is the mechanical part of the whole thing, that where you do the algebra, everything. But there is a basic idea of contour integrals, that there is a Cauchy's theorem, and how we utilize it, how we exploit Cauchy's theorem to do integrals. That I think was not captured by most of you. It was you were not really using. So that's one thing I would encourage you guys to go over again. I don't think I should go over here. We should move forward. We have only about 3 weeks remaining, so we should proceed. But I would say that there will be a final exam. So how about this? I will ask a contour integral question in final. So that should motivate you guys to look into it more. And yeah, that's what I would say. And yeah, coming to this integral, so this is a contour that's there. Okay, so that's here C. So it starts from here and ends there. So that's it, integral. But this is a Z plane, right? So that's integral is dz over z. Right? And we are actually, this is a path integral on a contour, means that if you're in a normal space, it's along a path. The path is specified, clearly specified. So on this path, what is the variable that is changing? That's one thing you can talk about. So this is a z plane. So substitute z is equal to r e raised to I theta. And it is this theta that's changing. It's not r that is changing. Is that clear?
Yeah.
Correct. So that's the important piece in that. And then we just have to do this integral. So this is currently on the contour C. We don't. So this is the C, particular C. Right? Now just substitute it. Do everything like normal integral. This is like a substitution. R is constant. That's your R. That's your constant R. E raised to I theta exponential. When I differentiate, I get an I e theta. Right. So this was so this is the first step. So it might be hard. Why am I doing that? Because I want a variable which spans that contour. Right. And theta is that variable. And from that point on, now I know that theta is equal to 0. theta equal to pi, and dz is r I d theta. I want to write everything in terms of theta. Z is r e raised to I theta. Is that clear what I did? And then realize that this cancels out. So R is not even there. It doesn't matter whether I was at a very large R or for that matter, very small R. I can go as close to the pole I want to, but that's not important. In this case, it is irrelevant. In this case, it just cancels out and you have I times 0 to pi to theta, that's I pi. That's it. That's all that was needed. And the question, of course, had a 2 pi I. So, is that clear? So, like, don't get carried away with all the information that you're carrying. It's at some level, it's just basic, simple things I'm asking.
I missed that integral part.
Yeah.
That limit range, I didn't get
Correct.
any examples.
Yeah. Like it was not a tricky question at all. And sometimes I do understand that sometimes in exam you do ask tricky questions and you think, no, it cannot be. But it was just this much.
I actually tried it this way, but I thought Ithika is going, this one is going to, so.
Yeah, then the confidence comes, right? Yeah, then you were not confident. Yeah. Sorry, yeah. But that's all I meant. Yeah. And why did I ask that? Because this is what you do in a normal bigger homework, right? In a homework problem, it's a complete problem. But somewhere in between you do this. Like you break it into C1, C2, C3, and then one of the contour contributes exactly like this, right? And you do that. So I said, okay, I don't have time to ask you the whole problem because we have only 1 hour. So I picked a small problem out of the homework.
I have one question. It is not exactly 0 to pi.
Yeah. So you can put whatever you want. Let's say this is delta 1, right? And this is delta pi minus delta 2. Right. So this is pi plus pi minus delta 1, right? And then minus of pi delta 2, or this is delta 2, this is delta 1. Fine. But now I have to specify your delta 1 and delta 2. My statement was that it is almost tiny, it's small. Actually make it 0. Why I put that gap there was that if I make it, so this was the reason why I put the gap there. If I do it like this, then there could be a confusion that there is a contour here also, because that's a line already there. So that was the reason why I put that. If you want to make it delta 1, delta 2 really tiny, you can take the limit at this point. Pi is really large, right? 3.14 is really large compared to whatever small you go, but then it's okay. Like reasonable confusions, but yeah, I mean, you will grant that I was okay there, right? So, okay. And yeah, rest of it, I think first one was roots. Most of you got it right, but I think when it came to plotting, yeah, some of you guys couldn't plot it. That was I was confused about it. You got the solutions right, but that means you were very algebraic. But then you didn't know how to visualize those things, so that was surprising to me actually. So typically, I mean, the way to say it is that I mean, this is for yourself. I'm not complaining here. I try to not preach. One way to look at it is that if you have the algebra clear, and if you're not able to plot, that's a self-assessment. You can say that you haven't put in enough effort, that you're not able to visualize it. Right? It's easy to go through the algebra and have a clear understanding, but if you cannot visualize it in some form of your own, it could be interpreted as, oh, you haven't completely mastered it in a sense. But it's always there. Many of the things even I cannot visualize. So that's just a small. Okay. So, the grades. Again, there are 4 people. It is hard to report the grades on the class. So we have this is the total. So this is complete total. Like all exams, all homework, everything. So highest is 93, 89, 81, 73. So, and I made a curve. Basically, I gave 10%. So A was equal to 0.1. 10% of what you lost, I returned back. It was actually not really relevant because most of you have almost 100% in the quizzes. So it's surely more than 90%, 90, 97, and 100. That's a great. So, but still, I gave 10%. So I think since question was reasonable, I thought 10% is sufficient at this point. This became 91 because of that. 83, 76. Right. So that's the distribution, but that should not. What I usually say is that there are a lot of things that happen by the end. There's a lot of curving that happens, so don't give up. Right? Keep trying. I mean, I'll just keep trying to understand. Like often it happens that there are 2-3 courses you're taking and you have to pick, right? At this time, you have to say that, okay, I can study only for one course, right? So you have to decide. So that's the reasoning for giving all this grades. So you can actually prioritize your time. But I would say this may not be completely indicative of what grade you will finally get. But still, at this point, if I had to give grades, this will be A. That's one possibility, but I don't know. There are a lot of things that happen.
Yes.
Yeah, I have a question about the grades. So I know that we talked about, this is an additional midterm.
Yes.
How was in the syllabus? It's like a 20%, I think, for the midterm weighting.
Yeah, this will be equally distributed.
Okay.
Is that okay? Was that? Is there anything else I said? I'm forgetting myself. All right. So, is there anything you guys propose? So we will have 3 midterms. I think midterms have a total of 40% is the distribution for midterms. So currently it is 20-20. So now 40 will get divided by 3 and equally distributed. Is that fine? Right. Like there is a someone would say that pick the top 2, right? So that's one thing one could do, right? But let me leave that and not do that at this point. Okay. So I don't plan to do that. I usually don't like dropping exams. That's my personal thing. Exam, I think, is too. And usually, if it is one exam, I understand. But when it is 2 or 3 exams, and there is some consistency, that's okay. So exams, I usually don't drop. Well, let's keep going as it is now. Okay. I want to sort of, this was a hard thing to do. I started introducing a little bit of quantum mechanics, and now I want to give it, I want to stop it, right, so that I can move forward. So it's a short example was a little hard for me to get, but I think I had a clear picture of what I wanted to do, but it's time seems to be short for. Okay, so I'll do it. I won't exploit it too much, so it will be just introduction, and I will try to introduce the idea of what we mean by in quantum mechanics. Often we say that if you make a measurement,
Mhm.
it disturbs the system,
System.
right? It's no more the same.
What function collapse? Mhm.
The function collapse, yeah, that's the interpretation, right? But I'll do the mathematics of that, what exactly is causing that. So basically the idea of vector space. So the main point is that if I think often, yeah, I think this was a title of a paper Schwinger gave. If you have, so there is this rhyme, and there's an English rhyme which says Humpty Dumpty sat on a wall, Humpty Dumpty, yeah. Humpty Dumpty had a great fall, had a great fall, and all the king's men and all the queen something could not put Humpty Dumpty together again. So that's the important part. They could not put together again. So the comparison here is that if you measure a system, you can never put it back to the earlier system. Quantum mechanics, you can never put it back in the state before this. So measurement really disturbs the system. So we want to see what that means, or at least what that conveys in a more precise manner. And what's the idea? Okay, so and let's. Oh yeah, I had fell about the midterm 3. That's some announcement. Is there anything? What is the grades? Yeah. Homework. Homework. 8 is due tomorrow, no, Tuesday, November 9th.
Yeah.
And midterm 3, oh, I have not even written. Midterm 3 is the Thursday before Thanksgiving. So that's what we agreed on. Oh, we didn't agree on the date. is it?
Actually, sorry, I was just gonna say we don't, as far as like Thursday, the 11th, we don't have class, I don't think. Like the campus is closed for Veterans Day. I believe.
Yeah.
Oh, I see. So what do we do?
But I think, yeah, I can't remember when the break is. I think next Thursday is the 18th.
No, 11th is it's
Previous
the
one.
week previous week.
Okay,
So
so-
how about 18th, right?
Mhm.
November 18th is a Thursday. The 9th,
Yeah.
11th. Right? Is that good enough?
Oh,
Are you leaving?
I'm the ceremony to attend. I have a niece born in Atlanta, so
Okay, so you'll be going early.
yeah, maybe 18. I'm not sure though. They had it 11 or 12, but now they reschedule it again. I don't know. So 18, maybe 17 or 18. So
Okay, this is getting hard.
I'll tell you today after the class. Can I confirm?
Yeah, can you guys get together and get a Thursday? Okay. Thursday or any time actually, any evening, any one of the evenings. I don't care which day.
Mhm.
Or it doesn't even have to be any evening. You just have to get together sometime
Right.
for an exam, right? And yeah, is that okay?
Mhm.
So contact Rob also, right? He may not be,
Yeah.
he has to be available.
Mhm.
So yeah. So between November, like preferably in the week before Thanksgiving, so that it's not too close to this time. This midterm, it's not too far from the, or it's not too close to exam either. Right.
When will be the final?
Oh, final exam.
7:39 or-
Final exam. Yeah, did you check December 9th? Yeah, that's
I might be getting confused though. I have three finals this year.
Okay. Okay. I did look it up. I think it is Friday. Friday would be, so we just now. So, oh. Probably. Anyways, check it quickly and so then I can also write it down.
December 10th.
Friday. Okay.
There's also a December 3rd, but I don't think it's that early.
Midterm start on December 8 to 15.
Yeah, it cannot be December 3rd,
So the Friday is December 10th.
8 to 10. Okay, Friday. And midterm 3, we are still debating. Okay, with that, it's a lot of time. Man. Yeah, so we talked about eigenvalues and eigenvectors of sigma x, sigma y, and then I said this is all just two situations of a much more general picture we have. This is what's the idea of vector space is. And in a vector space, you can choose your own coordinates. Like, for example, take the two-dimensional system who says x and y is important. You can rotate it, and any rotation gives you a basis vector. So similarly, let's begin with a so-called, we'll call this the Hamiltonian. Yeah, so let me begin directly. Let's say sigma theta phi. So that's a Hamiltonian. Hamiltonian is the energy domain, right? Is equal to if what we want to talk about is a magnet in the presence of another magnet. Okay, why I say that I'll give it in a minute. Remember, we talked about you know that Pauli matrices are related to spin somehow. Spin is angular momentum. If you have angular momentum, it has a magnetic moment. Okay, so basically anything that is spinning, think of a magnet. How does a magnet work? Like, how will you generate a magnet? Yeah, or how will you? Another way to look at it is that this is how I ask typically. Earth has a magnetic field. Mars, does it have a magnetic field? Planets in general, does it have a magnetic field? How would you, what is the requirement for a magnetic field? How is a magnetic field generated by a planet? And the moment you start thinking about that, then you say that, okay, let's come back to the lab. How do I create? Suppose I want to create a magnetic field. How will I create it? You don't have a North Pole, right? It's a North and a South Pole. So either you have a magnet, but in general, you typically have currents going around. Current is a charge going around. So anything that goes around creates a magnetic field, any charge that goes around. And that has to do with angular momentum. So anything that has an angular moment or any charge that has an angular momentum has a magnetic moment. Okay, so that's the basic idea. And now we want to talk about a magnetic moment in a magnetic field. That will bring in the spin, that will bring in the Pauli matrices, right? And that will have quantum nature for this. So that's what we want to talk about. So that's a broad picture. So Hamiltonian energy is magnetic moment dotted with magnetic field, right? And magnetic moment is equal to Q over 2m, this is a charge, times angular momentum. J itself is orbital angular momentum plus spin angular momentum. Is that clear how things are there? So the energy depends on magnetic moment depends on angular momentum has two pieces. One is an orbital, like velocity dependent quantity, velocity and position. This does not have any velocity and position. The spin, we will talk about a particle. We'll talk about a half spin. This is an H bar in it. That's the signature of quantum mechanics. And this is a matrix. That's a sigma matrix. Okay, or the Pauli matrices. But at this point, it is not necessary to say that this is the rectangular coordinate. So this is just a vector, right? It could be in any x, y, z is just a choice you make, right? It's, at this stage, it is some vector pointing in some direction, right? And let's put this all back. Let's say this is equal to 0. Let's say we are in the coordinate system. We sit on the electron itself if you really want to think of it like that. So L, you can always switch it off. Let's pretend that we are interested in the effects of the spin. Right? So then you put it back here. So there is an h by 2, so q h bar over 2. So this becomes minus of some constant h naught. So where h naught, some constant, some h naught times sigma, where h naught is all this constant to the right. So it is q h bar over 4m. Clear? So, what is sigma? For a moment, let us actually go into this is a scalar, first of all, sigma dotted with b. So once I calculate it in one coordinate, it should be the same in every coordinate system. Right? It should not depend on the rotation. It's a scalar. So let me calculate it in the rectangular coordinate system. In this, we have a particular representation. So this is 0, 1, 1, 0. I hat plus 0, I 0 plus 1, 0, 0, minus 1, and 8. And B, yeah, that's what I want to say. Actually, put this B also in it. Okay. So there is this magnitude of the B also has been pulled out into that. So only the direction remains. So that makes this a dimensionless quantity. So this should be B hat. Is that clear? Yeah.
So it's just a general magnetic field.
It's the usual magnetic field. Yeah, normal magnetic field. Ah, okay. I should actually, yeah, no, I should, no. This is an impossible magnetic field. How about that? Okay. This is a very fine, this is a good question. Okay, how about this? Give me a minute, I'll come back. Yeah, okay. So let me state this first. Let's say B, so magnetic field B, I say is B itself times a direction or hat. That means I'm claiming that it can be in any direction, but I'm saying that this is wrong. I'm going to very quickly in a minute say that it's wrong, but let's do it anyway. So that's our hat now. So this is our hat. Changing our hat. And our hat is sine theta, sine phi, I hat plus sine theta, no, sine theta cosine phi, right? Sine phi j plus cosine theta k. Okay. We saw that this quantity, when you evaluate this is equal to cosine theta, sine theta e raised to minus I phi. This is sine theta I phi. And this is minus cosine theta. That was that matrix this we did last time. Is that clear how I get this? if I were to put this in there, this in here, and this in there, notice that first term add up, right? 0 plus 0, or 0 times this, 0 times this, plus 1 times cosine theta. That's cosine theta. Right? Is that clear now? Okay, do it slowly. You guys are staring at me. Let's do this slowly. We did this last time, right? Okay, so this is equal to this dotted with this, right? So 0, 1. So this is 0, 1, 1, 0 times sine theta, sine phi. That's how I'll do a dot product.
Yeah, got it.
Correct. Yes. So this is 0 minus I 0 sine theta sine phi plus 1 0 0 minus 1. Good, right? Now it's clear. Right, and then this is 0 multiplied by this, 0 multiplied by this, 0, 1 multiplied by that is it. Yeah, so now I can write this as sine theta e raised to minus phi sine theta. So plus. Very clear?
Yeah.
Okay. And so now let's go back to the question as to, okay, now you have, so this is a real problem we're talking about. This is what is called Stern-Gerlach experiment. So I'm setting up that whole formalism for it. So what you're doing is that you take a beam of or a lot of atoms which have this spin and put it in a magnetic field. And in the model I have built, I have said that the magnetic field is of this kind. Right? Sometimes you say magnetic field is constant, sometimes you say magnetic field is. I have told that the magnetic field is of this kind. Its direction is r half. This is B. But then I say that there is something very, very fundamentally wrong. What's wrong? What's wrong in the magnetic field? What's the big deal? Distance from the
Like from the origin.
distance from the origin. Not clear.
I guess the magnetic field doesn't seem to the strength of it doesn't seem to fall off at any.
Yeah, but solenoid magnetic field remains constant, right?
Yeah, that's true.
That's okay. Yeah.
There's no change in direction.
Direction.
Direction, yeah, it is radial, right? It is radial. So the magnetic field is this, right? But it's constant. Right? This is constant. I mean, it's hard to show it as a lines. Okay, directionally, this is a wrong magnetic field lines. Okay, there's a lot of wrong things happening. This is not this. Why? Because its intensity should, here the intensity is increasing. Density of lines usually represents intensity of the magnetic field, but it's not, right? So let's say lines, right? Let me show this lines. So just let me show this as vectors. It's the same line everywhere. What's wrong in this? What's the big deal? Why am I saying that it's wrong? I'm saying fundamentally wrong. Some basic principle is getting violated, like something as basic as energy conservation or something like that. But it's not energy conservation. What's a big property of the magnetic field?
Del cross B is 0.
Del cross B is 0? No, it's not. Del cross B is 0?
Del dot B.
Del dot B
yes.
is 0. What does that mean?
Magnetic field coming at a point is equal to magnetic field going out of this point.
Yeah.
So, and that's why divergence of magnetic field is zero.
Divergence of a magnetic field is so magnetic field has to be divergence less.
Yeah.
Okay, and you even said it in words.
Yeah.
Correct. So is this okay? What's wrong with what you said and what I've drawn?
Clearly divergent.
There is a divergence, right? Because at this point, they're all coming out, nothing is coming in. So you said whatever is coming out has to go out. Right? At this point, it's only going out. There's nothing coming in, right? So this has a divergence. At that point, there is a divergence. This is not allowed. This does not satisfy L dotted with B is equal to 0. It's not 0. In fact, it's a delta function. It's a delta function right at that point. That is the contribution. But except at that point, everything is also fine. So I'm you're going to anyway do this, but one can say that okay, we are only talking about some region. You don't really create this magnetic field. Surely not. We cannot create this magnetic. But in the experiment, you will see that it's not really spherical at all. You're just analyzing it for one magnetic field. Okay, so that's it. The way it is portrayed, it seems like so you shouldn't take it too far away. Like don't take it as a fundamental magnetic field and proceed. In our experiment, you will see that it doesn't really. But what would change is that this leads to the idea of Bloch sphere. BLOCH, or the Poincare sphere. So these are our same ideas, which take the fundamental nature of this Hamiltonian and work on it. There you should be careful that this has been used. This is a monopole. This is a magnetic field that assumes that monopoles exist. Magnetic monopoles, when you say that there is a divergence at that point, that means there is an north pole there, right, that is creating the magnetic field, which is not true. So it is hypothetical in the sense. So Bloch sphere, Poincare sphere, whenever they come with conclusions, you should be careful about this. And it is used very much, but as a theoretical framework, it's great, but one should be careful as to what are the implications of this. Okay, so with that, let's proceed. This is our magnetic or interaction energy at this point. And so if I were to write H of theta phi, it's easy. Hamiltonian is basically equal to minus H naught, right? That's all there is to it, right? That's all. And it's a matrix, right? The way it sits, it's a matrix. And yeah, and if it's a matrix, just for completeness, what are its eigenvalues? Eigenvalues, just for your information, is plus or minus H naught. If you were to calculate the eigenvalues of this, it will come out plus or minus 1. So since there is H naught, it's plus or minus H naught. And I should say minus H naught times plus or minus 1. That's better. Because otherwise minus becomes the opposite. The minus becomes, or the plus becomes the minus value. So, and the eigenvectors now is, so now there are lots of theta and phi dependence, right? So I'm going to call this is the eigenvalue associated with the positive eigenvalue, and it depends on theta phi. Is equal to, it is sine theta over 2. The sine theta, no, sine theta. Let's do this as a homework. It's true. Let's check it instead. You guys have it? Mm-hmm. Minus. Yeah, is this correct?
The first one is correct.
This is also like you can always, it's a phase dependent quantity, right? So I can always pull this e raised to I phi out and make this correspondingly different. So this together should be 1, that is all that is needed. Like I can always pull out a phi, right? Is that clear?
Why is one is minus and one is plus?
It doesn't matter. So that's what I'm trying to say. If I pull out, so this is also equal to e raised to I alpha 1 I pull out the phi over 2. Okay. E raised to minus I phi and sine theta over 2. That's it, 1. That's also okay. Because I can pull out a phi, right? I can, this is a phase. So this is also fine. Does that answer your question? It doesn't have to be minus. I can pull this out and put this here. But the total should be the same. Like if this is plus, like the overall phase should be, it's only relatively I can speak over. Does that answer your question?
I mean, are you multiplying or?
This is multiplied. Yeah, this is multiplied. Is that the question?
Oh, now good. I thought maybe those are metrics.
No, that's not. It's some eigenvalue. Oh. All right. Helps.
Yeah, now.
That's certain. Yeah, I have to leave some gap there. Okay. Is this clear now? Question?
You have an I in the top exponential. Did you pull that out when you pull out the
This
5
side?
or 2? Yeah.
This is I times that. No? What's the confusion?
Well, yeah. So I thought when you pulled it out, you would have pulled out the I as well. That's what I was.
I did pull out I. Oh, but there's a bracket, right? Parenthesis. Is that the confusion? I'm having.
No.
What's the error I'm making? E raised to I by 2. Is that right?
Yeah. It's just, yeah. You just have an I in the eigenvector. So I didn't know why there was an I there.
This is not I, this is 1.
The one above that, there's an e to the negative I phi. So I thought that the I would be pulled out.
No, right? Because okay, I pulled out an e raised to I phi by 2.
Mhm.
So I multiply by, so e raised to I phi by 2, I pulled from there also. So it's already a e raised to minus I phi by 2. If I had to compensate for this, it is e raised to minus I phi by 2, right? If I pull out an e raised to plus, I have to provide a minus. Right? So this plus this is equal to e raised to minus I phi, right? Because it's in the argument of the exponential.
I see. Thank you.
Yeah, I think it's okay. Yeah. Okay. Okay. So let's leave it to that. And the other eigen vector is equal to e raised to another phase, and this is minus sine theta over 2, e raised to minus I phi by 2, and so sine theta over 2, e raised to I phi. And as I said, the phase, how you distribute the phase is actually a choice, and that one you cannot help because of the phase dependence. Eventually, we will not even bother about the e raised to I alpha 1 alpha 2. So that's your eigen values and eigen vectors for any theta. Okay. So now let's say we often say that in the basis of sigma x, basis of sigma y, right? What do we mean by that? Let's give it a slightly different meaning in this particular context. Oops. So when we say that magnetic field, so theta and phi is the directional magnetic field. So let's say theta is equal to 0 and phi is equal to 0. Right? Think of a sphere and you're on the North Pole, theta is equal to 0, right? And phi then doesn't have any meaning. So let's say phi equal to 0. Is that clear what theta and phi on its sphere is? Right? Have a spherical coordinate, theta and phi. Right? Okay. So So let's maybe so if we have a sphere, so that's the North Pole. Right. So this is theta equal to 20 degrees, let's say. And this is the equator. So this is theta equal to 90 degrees. This is probably theta equal to 150 degrees. Is that okay? And it goes all the way to, this is the Earth, let's say, sphere, and the longitude that we talk about typically. Right. This is pi. Right, as you go around. So for example, on a Google map, if you look for the coordinates of Carbondale, it will have some angle theta and some angle phi. The only difference actually is that on the Google coordinates, we measure with respect to the equator. Right. So this is the equator. So this is the measurement. So that's our angle theta. So you would say theta minus pi by 2. So Google talks about theta minus pi by 2. So when for North Pole, it will say it is, why is it minus pi by 2? So theta equal to 0 plus pi by 2. Is that what it is? Yeah, plus pi by 2. And it is, no, it's minus, right? Yes. Yes. Okay. So if it is pi by 2, then it is 0. Okay. I think so. Okay, let's not. But you get the point, right? Okay, so what is theta equal to 0? What is this Hamiltonian? That's what I was talking. This is 0, 0. How much is that equal to? That's minus h naught. So let me have a new notation. This is sigma theta phi. So that's cosine theta minus cosine theta, so that we don't have to worry about the Hamiltonian. What is sigma 0, 0? One, right? So that's sigma z. Right? Yeah, so you can pick your values from. So now tell me, now that I told you that this is sigma z, tell me what is sigma x. For what angle do you get sigma x? Right, so you want to set theta equal to pi by 2 maybe, because that cosine theta is gone. So when will you get sigma x? For what angles will you get sigma x? Pi by 2 and?
Zero.
And 0, right? Because you want to kill that exponential, so that's 0, right? Where is that? If you were to have a coordinate system, right now I'm going to draw not the Earth, the coordinate system. This is your x, right? That's your y, and that's your z, right? And this is a general vector R. So that's angle theta, and clear? Yeah. Clear? Right? So there is sigma x. I have to put theta equal to pi by 2. It's on the xy plane, right? And phi is equal to 0. It's in the direction of x. Right? Sigma x. Right? Sigma z is theta equal to 0. It's in the z direction. Now let's say what is sigma? So where is sigma y?
I over 2. Yeah. I over 2.
Right. So one would think that you're probably looking at the diagram and telling it, but now let's go back and see whether it is really coming out that way or not. If you put pi over 2, that's gone. Sine theta is 1, and exponential of minus I pi by 2 is indeed minus I. So this is indeed pi by 2, and this is pi by 2. Right. That's nice because that seems to suggest that these matrices are just special values of a bigger geometrical object. Right? There is a lot of matrices which I can pick. Okay. So now, so that should be the idea. These are just special. We can actually take any angle at this point, and you have a polymatrix, and that also tells that you can take any 3 coordinates, right? Who says this is a? You just have to have 3 independent vectors, and any 3 independent vectors in 3-dimensional space is good enough, and they will be a set of polymatrices. They will satisfy that algebra also. Okay, so that's good. So now let's actually do an experiment, right? So what we're going to have is, so this is what is called Stern-Gerlach setup. Stern-Gerlach. Experiment, I think. Experiment. Yeah, experiment. Apparatus? Okay, apparatus. I wrote it as experiment. Setup of apparatus. Okay. So what we do is we take silver atoms, and silver atoms happen to have a magnetic moment. The atom, we're not talking about a nucleus or an electron or a proton. This is an atom itself, and its nucleus or silver atoms happen to have a huge magnetic moment. Okay, so, and it's, if you have a magnetic moment, remember there is a angular momentum and S comes in. So the whole silver atom has an S associated with it. Okay, so that's the only point. So it has a magnetic moment, and that's the important thing. You know, you take a box of it. This simplistically speaking, experiment I'm sure has a lot of more challenges. Take a small 1 centimeter by 1 centimeter by 1 centimeter cube, fill silver atoms to it, and heat it up. Okay. Heat this up. The burner, heat it up, and this becomes silver. Yeah, there's a lot of silver atoms in here. Right? Since it is really hot, let's say 1000 degree Kelvin. So this is temperature T is equal to 1000 degree Kelvin. There are a lot of silver atoms going around everywhere in all directions. Then you make a small hole here. Right? The moment you make a small hole, there are all the silver atoms starts getting outside in all directions. Their velocity is distributed in all directions. You put a small hole there, and they all get blocked. There is only these kind of atoms, but still they might have a spread. Put another hole, and then you have controlled its velocity sufficiently. So only those atoms that have a velocity in the z direction, let's say z direction is that, they come out. Rest everything is blocked. That's amazing. So we are selecting, we are basically filtering all the atoms that has a velocity in that direction, a velocity. But still, its velocity could be anything, right? Velocity could be 0 between, there could be a whole distribution between 0. It's velocity not chosen. There are ways to select velocities also. We can actually make it very reasonably precise, but statistically speaking, most of the atoms will have a velocity close to 1000 degree Kelvin. Velocity close to half mv squared is equal to temperature, right? So it will be close, but there will be, of course, a distribution around that. But what about the magnetic moment? They will be everywhere. There is no control on this magnetic. This doesn't, just because they're moving around, doesn't select a magnetic moment. So they're random. It could be, each atom has a magnetic moment, has a special direction, but they could be pointing in any direction they want. Okay, so that's the idea. So you have a beam of silver atoms, beam of magnets, for simplistic analysis, which are anywhere oriented in any direction you want. Statistically speaking, it's zero, right? Averages are zero. Now you put a magnetic field, but you don't put a normal, any kind of magnetic field. You put a north pole, which is very pointed, right? It's a cone kind of structure, and the south pole is kind of spread out. Think of a nail-shaped structure where the north pole is in the shape of a cone. What that does is that any edge usually has more magnetic field than a soft side. It's like electric field, right? It is stronger magnetic field. What that means is that there are more number of lines. So magnetic field looks like this. Right? Remember, intensity of lines shows you how strong the magnetic field is. That's your magnetic field. The basic idea is that there is a gradient of magnetic field. It's not a constant magnetic field, there is a gradient of magnetic field. And this beam goes through that. And we would like to know what happens to this. In fact, we will keep repeating this. Okay, we will do this. Once it goes through, then we will keep another one. But now we will change the orientation. Remember, this is a magnetic field dependent quantity, right? So first we will put it in some direction, then we will put it in another direction, then we'll put it in another direction. So we'll put 3 of them. Like this will be our detectors, if you want, and we will put it in multiple times. Okay, so we'll come to that. But let's talk about what happens in one detector. Okay, once or in one setup. So this is what we will be calling external setup. This piece. There is a beam and it goes through them. Okay, so there is a magnetic field. So what happens to a magnet in a magnetic field? It experiences a force. What's the force it experiences in a magnetic field? What is the force experienced by one magnet in the presence of another magnet? There's a magnetic field. What's the force experienced by the magnetic moment?
Velocity, electron.
That's an electron, right? But this is the magnetic moment. Magnetic moment is like a magnetic dipole moment. Right? So what you're trying to say is force is equal to QV cross V, right? Right. That's good, but this is charge, right? This is a neutral object. This is a neutral atom. So this doesn't really work, right? So what is the force on a magnetic moment?
Magnetic moment the product with the magnetic field.
That's energy. That's a scalar. That's not even a force. It's not even a vector. Right? That's the energy, right? That's what we said. Energy will then dot to the D.
It's torque.
Huh?
It's torque.
No, torque. It will experience a torque also. That's the next question. What about the force? You have the energy. So what's the force? If you know the energy, what's the force?
Differentiate the energy.
Yeah. Yeah, I think you guys are saying it like gradient of energy, negative gradient of energy. Remember, force is a manifestation of the fact that energy tries to be minimum, right? So force is negative gradient of energy, in this case, minus m dotted with d. Right? M is pretty much constant, so it is only b if it is changing. If b is not changing, if b is uniform, what is the force?
Both are constant.
Now, if m is constant, m is usually not dependent on the coordinates, right? M is a property of an object. It doesn't depend on the coordinates. So this never depends on, this is not a gradient dependent one, but this can depend on position, right? At one point to the other point, there is a change. If B is uniform, what's the force it experiences? Force a magnet will experience?
Depends on mass.
Is that correct? For example, what you're saying is that there is a uniform magnetic field in this room. You bring in a magnetic compass, right? What's the force it will experience? Is it 0? Is it 0? Yes or no? Don't get confused. I might be tricking you.
I mean, according to Faraday's law, if there is a constant magnetic field, we are not getting any electromotive force. The magnetic field has to change with time.
Yeah, but this is, yeah, that's all correct. You're right. But we are not going there. I mean, we're not, there is no time dependence in magnetic field. Like you're thinking more than, your correct statements are correct. But I'm just saying that in this room, let's say you have a uniform magnetic field. Uniform magnetic field. I bring in a magnet. What's the force it will experience? Is it going to be 0 or non-zero based on your simple earlier knowledge?
No, non-zero.
Very sure?
Yes.
Very, very sure?
Yeah.
It is 0. So it's equivalent to, let's say, if you have, let's take a dipole, okay? There's a negative charge, there's a positive charge, right? And if I put an electric field in it, what's the force on this? Uniform electric field. This is a dipole, right? That's clear.
Mhm.
What's the force on this system, this full dipole? So you will say that there are 2 charges. One is in this direction. This pulls it this way, Q times E. This pulls it this way, Q times E. If it is uniform, these 2 cancel out. If it is non-uniform, this is slightly more than this, correct? Because it's non-uniform. If it is uniform, it is 0, right? Now, what is the analog of this in magnetic field? You put a loop, right? What is a magnetic moment? You put a loop. Let's say like we do this, right? I mean, a current carrying wire, right? In a magnetic field. Is that clear? It's going through the loop, right?
Mhm.
What does it try to do? Like there will be a force on this side, there will be a force on this side, that side. They will all cancel all the time. If you actually calculate it, it's a little tedious. Little tedious. We do this in class, but if you allow me not to do that here, it'll actually cancel out. Force will be 0 in a uniform magnetic field. That's why this is shaped in this manner. Because if it is 0, then it's not interesting. We really want it to deflect. Right? We want a non-uniform magnetic field. If it is a uniform magnetic field, it doesn't work. Right? So we want a force. So force is dependent on the change in magnetic field. And it doesn't care for M. Since it's an atom, it's a point object. It doesn't change from one point to the other. So if I were to choose B in the direction of BZ, right? So it is only the Z component of M that matters, right? And let me also say that B depends only on the Z direction. I made a lot of modeling there, right? I create a magnetic field, which is in the Z direction. And I also say that it depends only on the Z direction. In the sense, if I go this way, the magnetic field is constant. XY direction, it's all uniform. But if I go up and down, it depends on the position, right? Then there is a lot of simplicity because since it is in the Z direction, it is only the Z component of the magnetic field that is, notice Z component. It's a projection. Even though the magnetic moment could be anywhere, it is a Z component. That will play an important role in the analysis, right? So this is going to be, that's negative, negative, plus. So it is mz times, this depends only on the derivative with respect to z hat. So this is d by dz, and it's in the z direction. Is that clear? Yeah.
So Earth's magnetic field on us is not uniform.
It's not.
I'm asking if it's uniform or not.
Let us say it is uniform. Suppose it was uniform. Who says there is a force acting on a magnet? It only rotates, right?
Mhm.
So it is, first of all, it's not uniform. Let's begin with that.
Okay, right.
It is like our magnetic field, our Earth's magnetic field is this way, right? But in the region where we are standing inside this room, to 2 significant digits is probably uniform. Right? It's probably uniform, right? So for our purposes, it is to 2 digits, it is uniform inside of this room. But then you say that, and that is why if when you have a magnet, you don't get pulled, right, to one side of the room. What it does is that it rotates. It's a torque. It points in the North Pole. It doesn't get pulled to the North Pole.
I see.
Correct?
Yeah.
So if there was a force, it will get pulled to the North Pole. That's not what it does. It orients to the North Pole.
Okay.
So it experiences a torque, but not a force. And maybe that was the confusion that you were involved. That I know that I use the North Pole to check that orientation. So why is he saying there is no force? Okay, yeah. So that could have been the confusion. Okay, clear? Okay. So this is a detail in there, but this is the z component of the magnetic moment. So in whatever direction it is, it's only the component that matters. Okay. Torque, what it is? What does a torque do? It tries to orient it, right? So, there's something more to that. Let me not. So whenever this is an angular momentum. Torque is also angular momentum, right? dL by dt. Correct? Angular momentum or J, right? This is dJ is equal to, in this case, the torque usually is M crossed with B, and it will come out to be J crossed with B. Okay. That will be your equations of motion. Let's not go in there, but the idea is that if what happens when you have an equation of this kind, it acts like a top. And what is a top? If you have a magnet, think of a toy top. If you have gravity going down, what does the top do? It spins around the gravity. Whatever is the axis, it spins around it, and in fact, it's called precession. Right? It will precess around it. That's all the torque does, and that is what our magnet is trying to do when it is trying to orient, right? So what this will do is that, so there is a beam coming in. What are the 2 things that is happening? Because this is non-uniform, this will try to drift that way, right? In one direction, like wherever is that dV by dz, and depending on this component, but this component could be down or up, right? Because it's anywhere. So plus or minus, we don't know, but once it is there, it will actually either start going up or start going down. If to begin with, it was oriented with the gradient of the magnetic field, then it will try to go up. If it was to begin with, it had a component in this direction, then it will try to go down. And it doesn't have to be down, even if it was like this, then it's biased and then it will start going down. Is that clear? That's what. And while it is going down, it will keep precessing. So as you're getting drifted, think of I am a magnet and I'm in the magnetic field of Earth. I keep getting, actually these days this is happening, right? The magnetic activity of sun is very high these days. What actually that means is that sun is actually a lot of charges, right? Positive and negative charges. They keep spiraling on the magnetic field and reaching there, but not a good example because they are charges. So, but here we are talking about magnets, right? I'm really talking about a magnetic compass. If you had to put it, it will get drifted if the magnetic field is not uniform. And while it is drifting, it will keep precessing around the magnetic field, right? So that's what will happen in here. Now, what will happen? Okay, if you forget about the precision, let's talk about the force. This force, mz, is m cosine theta. So m times cosine theta. Let me take 5 more minutes still. So mz is actually m times cosine theta times dv by dz. Is that clear? Where theta is the angle the magnetic moments make with respect to the magnetic, with respect to z. That's it. So this is m. That's it now. Yes.
The W del Z.
Huh?
I'm confused about the W del Z and Z. Like we have it not absorbed there. I didn't know if there's
Tell that again.
like the MZ there on the force. So that has an dependent on
Yeah, so I can make it more precise.
sorry, I didn't know.
So notice that this is the z direction, and B has been chosen to be in the z direction, correct? So the magnetic field is in that direction,
Okay, I see.
Correct.
Yeah, thank you.
and its gradient also is in that direction.
Thank you.
So, and the magnetic moment is somewhere in this. In general, it is an arbitrary quantity. And this could be here also. It's completely random anywhere, but it will be somewhere around. If it is in the upper half plane, that is positive, right? And then it will immediately try to get drifted in one direction. If it is in the bottom half, it tries to be negative, and then it will try to get drifted in the downward direction. But what do we expect is whatever happens there, based on this bias, what will happen after all this drifts happen? Some should go like this, some should go like this, because the force depends on this. There is a cosine theta bias there. That should be like this, right? The peak should be something like this. There will be a lot of atoms here, less number of atoms. At least there should be one of them which doesn't get deviated. Like if the theta was pi by 2, for example, it is 0, right? Force experienced is 0, right? It's already aligned with the, that's why it is no force at all. So it should actually go and hit that. At least some should be there. Even if not, there should be more here, and there should be an equal distribution of. But experimentally, that's not what you see. Okay. Experimentally, this is what led to quantum mechanics. Experimentally, so this is theory, right? This is classical physics. What happens is that this sharp two peaks, and these are silver atoms. It is very easy to do this experiment because you keep a photographic plate. Have you seen the old photographic plates where you expose a quantity? Have you seen this? Oh, in the olden days, we didn't have digital cameras. Right? By olden days, I mean 20 years back, like 20 or 30 years back, there was no digital camera. So what happens is that light penetrates, and on the back side, there is a film, and that has silver coated on it. So silver, when exposed, immediately is very sensitive to light, and it will leave a mark. So this leaves a mark, and it's a really sharp marks. I mean, you can see this. I mean, these days, I mean, I've never done this experiment, but you can see this photographic plates from that experiment on the internet, for example, and you see this sharp plate. So this doesn't explain it, right? And the question is why, right? And that we will try next time. I was thinking of finishing it today, but I'll finish it on Monday. Yeah, question.
This is like the double slit experiment.
Yeah, this is exactly like a double slit experiment, but this is much more concrete in the sense we can actually analyze it. I shouldn't say much more concrete. It's exactly like the double slit experiment. So all the features of double slit experiment is there in this. So what do you say in double slit experiment? So typically the language is the following. Okay? Double slit experiment, we'll talk about this. So there is a slit, right? And light goes in from here, right? That's a photon, and that's here. If you were to close one of this, there is a peak here, right? If you close the other one, there is a peak there. But if you open both of this, the expectation is that that should have been, like classically speaking, yeah, this is slightly different. So the classically speaking, this should have been just like this, but instead you see an interference fringe. So here there is no interference. We talk about really quantization there. So how do you say this? Or okay, maybe let me say it in the language that's chosen. Okay. Yeah. So here's the so let's say there is a single photon going. Whatever that means, single photon going, and it is going through this. If you do not look at which place it's going, it will behave in a certain way. Okay, and let us say it will produce fringes. Right? By fringes, I will show it as like this. Okay, so that's one possibility, right? But now let us say that I go and look at the photon. Oh, which one are you going through, right? If I check on the photon that, and if I know that it is actually gone through this, then it won't give you this. That means what the statement is that if you make a measurement, okay, then the effect is different from whether you do not make the measurement. The same electron is going through, but the only difference is that I looked into it. Okay. That's a little hard because you're talking about photons and you say, how do you look at a photon? Here it is really physically possible. Here what I'm going to do is, I will have a beam of atoms and I will say, I will select, this is going to bend like this, right? I will select one of them. Okay, that will be my measurement. I can either let both of the beams go through or I can stop one of the beams. That's an easier experiment to do. And we will show that on Monday, algebraically, that the result will be different. And that's what we mean by measurement disturbs a system. That's a quantum meaning to that. But now I should stop. But yeah, sorry, I get distracted here and there, but I think hopefully all this will come together on Monday. Yeah.